A neural network is a machine learning model created by analogy with biological neurons operating in the brain.
It consists of a set of nodes, called neurons, organized into layers: input,
Hidden and output. Each neuron processes the input data,
transforms it, and passes the result on.
These models are used to solve complex problems such as image processing, text analysis, speech recognition, and prediction. How neural networks were created. The idea and early models. In 1943,
Warren McCulloch and Walter Pitts proposed a mathematical model of how neurons work.
In 1958, Frank Rosenblatt developed the first computer implementation of a neural network, a perceptron that could distinguish simple geometric shapes. Neural network crisis. In the 1970s, interest in neural networks declined due to the limitations of perceptrons. They could not handle tasks requiring nonlinear data separation. Renaissance.
The 1980s saw the emergence of multi-layer perceptrons and the error backpropagation method proposed by David Rumelhart and James McClelland. This made it possible to train more complex models.
Modern stage. In the 2010s,
deep learning boomed due to increased computing power and the availability of big data.
Architectures such as convolutional and recurrent neural networks have become the backbone of many applications. Current advances. Modern models such as transformers, the basis of ChatGPT, use complex structures to process large amounts of text, audio, and visual information, showing impressive results. Neural networks continue to evolve, becoming more powerful and versatile, making them an important tool for solving complex problems in science and business. The development of neural networks, from idea to current technology. 1940s, birth of an idea.
1943, Warren McCulloch and Walter Pitts proposed the first mathematical model of an artificial neuron. Their work explained how biological neurons could be modeled to perform logical operations.
1950s, first breakthrough. 1958, Frank Rosenblatt created the perceptron, a simple neural network for solving classification problems. The perceptron could learn by adjusting its weights based on input data. 1970s, crisis, AI winter. Models such as perceptrons proved to be underpowered for complex tasks. For example, they couldn't handle nonlinear problems,
leading to a decline in interest in neural networks.
1980s, Renaissance.
The backpropagation method became a key tool for training multilayer neural networks, proposed in the works of David Rumelhart and James McClelland.
This allowed deep networks to be trained and to handle more complex tasks. 1990s, integration into applications. Neural networks began to be used in real-world applications: speech recognition, image recognition, data analysis.
Specialized architectures develop,
such as convolutional neural networks, CNNs, proposed for image processing.
2000s, the beginning of the era of big data. Increase in computing power, video cards, and cluster systems.
Neural networks began to be applied to process large amounts of data. Training became faster, results more accurate. 2010s, deep learning boom. 2012, converged networks, CNNs, achieved breakthroughs in computer vision tasks, e.g., AlexNet's success at the ImageNet competition. Recurrent networks, RNN, GRU and LSTM for temporal sequences and text processing are developed. 2017, transformer architecture revolutionized text processing, leading to models like GPT, generative pre-trained transformer. 2020th, current achievements. Large-scale language models such as GPT-3 and GPT-4 demonstrate abilities in text generation, analysis, translation, and more. Multimodal models, e.g., DALL-E, CLIP, self-learning systems are actively used for autonomous solutions such as unmanned vehicles. Neural network and CVs. One day, a company decided to use a neural network to select candidates' CVs. The algorithm analyzed the questionnaires and gave recommendations on who to invite for an interview. After some time, the developers noticed that the system favored candidates with certain names. For example, if a person had the name John in his CV, he was more likely to be included in the list of recommended candidates. After analysis, it turned out that the neural network, trained on data about past successful employees, made an unexpected conclusion: most successful candidates had common names. This case caused a lot of laughter, but it also showed that neural networks can form unbiased conclusions based on strange patterns in the data. This case was a lesson in the importance of checking algorithms for such hidden biases, but it is jokingly remembered as an example of how even smart machines sometimes make highly unusual decisions. Today, neural networks are being actively developed and used in many areas. They literally live in our technologies, helping to make people's lives easier and more efficient. From the inception of neural networks to the present day, key stages and changes. Early stages, 1940s to 1980s, basic models and ideas. Emergence of ideas, the first concepts of artificial neurons, such as the perceptron, 1958, were simple mathematical models. Limited capabilities, early neural networks could only perform basic tasks due to low computational power and a lack of data. Revival of interest, 1980s to 1990s, multi-layer networks. Training using backpropagation. This method made it possible to effectively train deep neural networks, marking a major breakthrough. Practical applications, neural networks were used in speech recognition, medical diagnostics, and other tasks. Rise of deep learning, 2010s, powerful computing and big data. Deep networks, architectures such as CNNs, convolutional networks, and RNNs, recurrent networks, enabled advanced processing of images, text, and audio. Data boom, the increased availability of large datasets made training more complex models possible. Computational power, the development of GPUs and TPUs accelerated model training speeds. Current achievements, 2020's next-generation neural networks. Language models, modern systems like GPT-3 and GPT-4 can understand and generate text at a near-human level. Multimodality, models such as DALL-E and CLIP can process not just text but also images, videos, and sound. Training speed and automation, methods such as unsupervised and self-supervised learning reduce the need for labeled data. Integration into everyday life, neural networks are embedded in technologies ranging from voice assistants to medical diagnostic systems. Key differences between early and modern neural networks. Depth and complexity, early neural networks had a few layers, whereas modern ones have hundreds or thousands. Data quality, today's models utilize billions of parameters and enormous datasets for training. Intelligence, modern neural networks not only solve tasks but also learn new skills, analyze context, and deliver precise results. Versatility, next-generation models have become highly versatile, capable of working across different domains, text, images, sound. Future prospects. Efficient and eco-friendly models, reducing energy consumption for training. New architectures, continued exploration of transformers, graph networks, and other approaches. Autonomous systems, neural networks will play an even greater role in autonomous technologies such as drones and robots. The evolution of neural networks has made them a powerful tool transforming the world.